Alright, class. Today we'll finish chapter 15. The topic is the moment and angular momentum of a system of particles, as well as the principle of angular impulse and momentum. This is section 15.7 and forward, so we'll try to finish chapter 15, which deals with the impact. So the first topic is the relationship between the moment of a force and angular momentum. So this is section 15.6 from the textbook. Let's consider an example, a case study. And this will help us derive the equations and understand what's happening. Consider a satellite that's orbiting in elliptical pattern. This satellite has a mass m and is orbiting about the Earth. Well, the distance from the satellite at time, let's say t1, is considered to be r1 vector, and at time t2 it is r2, where the Earth is our reference. I'm going to call it reference O. Okay. Now we know there is an attraction force between the satellite and the Earth. Let's call this attraction force F. Since it's at location 2, I'm going to call it F2, and this is, again, is a vector. And also there's an attraction force at location T1, it's F1. Great. Now, so consider a satellite orbiting Earth, and this Earth has is at the origin, and let's consider this to be a 2D problem, right? Now, the moment of a force at any time, and let's call this force F to be general, at any time, which is also mean at any location, or at any location, R, right? And can be computed with reference to an axis that passes through a desired point, right? Let's say we want to calculate the moment of the force about the Earth, or about O. So the moment of force about O is simply, or the all moments, or the sum of all moment of forces about O simply can be done by calculating the cross product between the force and the distance between the reference point and the object that is moving. So this is R dot, right? Where Fr is the resultant force acting on the object at location and summation moment about O is sum of all moments computed about the origin O. Great. Now we know these are vectors, right? And the location, this is vector, this is a position. So R is the position vector. Now I can write these position vectors in its component Rxi plus Ryj plus, if I'm using Cartesian coordinate system, and Rzk, as well as the resultant force. I can break it down into its component, Fxi, if you remember from static, Fyj, and Fzk, right? So we know that. Now, this cross product, it's an operation. Just to remind you, from the static, you learned that the cross product, which is R cross F, R can be taken by using the determinant ijk, and you write here the elements of the R, Rx, Ry, Rz, Fx, Fy, and Fz, right? And this is a vector, so the result of this is gonna give you a vector, right? So this vector, if you remember from static, this determinant, it simply is equal to there's a method to do it. So you can write first I and minus j and plus k, and what's in here, parenthesis, is the determinant of each quadrant. So I'm gonna cover that, and this is the first term, so it's gonna be the determinant of this portion, so it's Ry multiplied by Fz minus Rz minus Fy. For the second part, and I have to remember the I, so it's going to be in here, Rx Fz minus Rz Fx. Here, it's going to be Rx Fy minus Ry Fx. So just to label that, Ry Fy, I'm sorry, Ry Fz, Fz Rz, and Fy. For the J, so this is closed, Rx Fz Rz Fx, and the last one is Rx Fy, and then minus Ry Fx. Right? So this is the vector. The magnitude of this vector is also can be realized from the cross product. So this cross product, which is, it's R cross Fr, right? And this is moments. The magnitude of this, which is, we call it also the norm, is equal to the magnitude of vector R multiplied, this is simple multiplication, by the magnitude of Fr multiplied the angle between them, which is sine theta. So theta is the angle between between R vector and Fr vector. So this is good to go for 2D problems, right? Okay, so the moments of this force F at any location is simply R cross the resultant force Call this is resultant force at any location. Recall that the resultant force is the mass by acceleration, right? From the Newton's second law, or we can write it as m. A is derivative of the velocity, right? Therefore, summation of moment is r cross m dv over dt, right? And the velocity v is a vector. Now we know that the mass and the distance are constants. Therefore, I can rearrange dt is equal to r cross mtv. Great. Take the integration of both sides. This is with respect to time, so this is from time 1 to time 2. And this is with respect to velocity, so this is the velocity 1 and velocity 2, right? But I don't like this form. I'm going to continue with some definition. Let r cross mv be defined as an angular momentum, h. An angular momentum calculated about point O, which is the same point here. So this is called the angular momentum. So this is by definition momentum. Okay, we define that. Therefore, if you take the derivative of both sides, rm dv is going to be equal to dh naught. So take derivative, both sides, you get that. So which means my equation 2 is simply T1 to T2 summation of all moment over the time equal to dh naught from 1 to 2. Now integration of 1 is with respect to h naught, it's h naught. So this is equal to h naught, and so you substitute 2 minus h naught 1. So in summary, I can say summation of all moment dt is equal the angular momentum at state 2 minus angular momentum at state 1, and this is computed over time t1 to t2. So we're going to call this the angular impulse. It's analogous to the linear impulse that we studied earlier. So this is angular impulse. We're going to call this, we already called this angular momentum. At state 2, which corresponds to time 2, and this is angular momentum at state 1. Great. Now, the way you calculate that is summation of all the moments acting on the object as it's going from T1 to T2. Now, let's take a look at this problem over here. So, what moments acting on this object? Well, the moment is the moment of the force, or you have a free coupling. There's no free coupling as it's going, for example, from state 1 to state 2. There is always a force acting on this. The only force acting on this satellite is due to the gravitational force, which is oriented or directed always toward the Earth, which means it's going along the vector r. And we know that we said that when that force, we're still examining this case study, we said that the angular momentum, or the summation of all moment in scalar form, is equal to the r multiplied by fr multiplied by the angle between them. So for this special case, for a satellite, just to be specific, so this is, in fact, this is called the principle of angular impulse and momentum. So this is, I'm going to call this, before I talk about that, this is called the principle of angular impulse and momentum. Impulse and momentum. Okay, so that's the principle. Special case, such as satellite orbiting Earth, as an example, and assuming that there is no thrust forces coming from the satellite itself, it's just orbiting using the gravitational forces F. So in this case, there's no free couple moment, the only force is the Fr. So this drops to the moment of this force. So the moment of the force from T2 to T1. So let's do this integration in much more detail. Now this is a special case. So from T1 to T2, so that's going to be equal to summation of all moments, because nothing happened in between, so it's a constant forces, so it's going to be equal at time 2 minus summation of moment time 1 equal to h naught 2 minus h naught 1. This is going to be F1 as a magnitude, or F2, I'm sorry, magnitude of R2, sine angle, which is 0, because we said the Fr is going along the radial, minus F1 R1 and sine 0. So the entire thing is dropped to 0, equal to h naught 2 minus h naught 1. That's going to give you h naught 2 equal to the h naught 1. This means because there's no angular momentum, so there's no moment or forces acting on the object. So this is called the conservation of, or we can say that the system has a conserved angular momentum, because it's equal. So this is called conservation of angular momentum. Okay, so when this is 0, then you have the angular momentum, which we defined before and after, or at any location, is, if it's conserved, then it's going to take this form. So in summary, we have described that the summation of all moments about the point is equal to R cross F, where we define that F is m multiplied by dv over dt, and that is this altogether becomes a derivative of the angular momentum. So the derivative of angular momentum about the point O, by definition, is equal to the summation of all moment. Now, so far we discussed for one particle. So what if we have a system of particles So keep in mind that the internal forces, the moments of the internal forces, will cancel each other within a system. So we'll end up with that the summation of all the moments acting on every particle is equal to the summation of the moment of these forces, where Fi is the resultant force. That's equal to summation of all the derivative of angular momentum. Also, to put things in perspective, just to summarize what we have done, is that the principle of angular impulse and momentum is equal to the summation of integration of all the moments from T1 to T2, and this is the angular momentum at state 2 computed about O, as well as the angular momentum about O computed at state 1. Let's take a simple problem. We have two identical masses, so this is a system of particles. We have 1 and 2 attached to a rod. We assume that the rod doesn't have any weight, so it's negligible. These two masses are under external forces, P10 Newton and P10 Newton. Together they cause rotation counterclockwise. And also we have a motor that is supplying torque to this rod, but this torque is a function of time, and it's increasing linearly. It's 8t Newton per meter. So we want to calculate the speed of these two spheres that is connected together at time equal to 4 when this system starts from rest position. Now, obviously, the principle of the angular momentum, impulse momentum, and can be applied here. Since we have a system of particles, we're going to compute the angular momentum for all the particles, computed about O. And then compute the moments about O as it's changing from T1 to T2, for all of them, and also for the forces, as well as compute the angular momentum after, right? So let's careful. So at the beginning, the velocity is 0. Remember, this is equal to R cross mv, right? So v is 0, so there's no need to worry much about what's happening with R and v, because v is simply 0. So this is 0. The summation of moments, there's two sources. There is the integration of AT, and also from 0 to 4, and there's also, during this time, from 0 to t, there is a constant forces that's supplied to the system, and this forces causes a moment, which is, if we want to compute these moments about O, it's simply, let's consider that counterclockwise to be a positive, first of all. So this is integration of AT is a positive. Then the P10 and P10 causes also rotation. So it has two components. First is 0.5, it's R cross the force P, and since R is equal to 0.5, and since P is orthogonal, right, so it's a sine theta is 90, or sine 90 is equal to 1, therefore the moment of this part is 0.5 by 10 plus this also causes another moment 0.5 by 10. So so we have 2.5 by 10. Or if you don't like that, you can say this is a coupled force because they are equal. So it's the moment produced by these two is 10 multiplied by the distance orthogonal to the vector p's. So it's 10. So I advise you to look back to static and look into the definition and how to compute the moments. So that's computed over that time equal to the moment or the angular moment after. The angular moment after is r cross m multiplied by velocity, right? Since similar fashion here, so because they are identical, so I'm gonna multiply by that 2 and I'm gonna end up with the r 0.5 multiplied by velocity, which is unknown at instant 2 or at time equal to 4, multiplied by the mass, right? So this is one equation with one unknown. You conduct the integration, it's simple, and that's going to give you a velocity of 10.4 meter per second. Okay, so let me do it again. This time I'm going to use a paper and pencil, so we reinforce the learning here. So this is summation of the moments for the system. This is at time 2, at time 4 seconds, and this is at time 1 second, 0 second, sorry. So remember that the angular momentum is equal to r cross mv, right? And remember that the moment is r cross f, right? This is a 2D. Anything off the plane is considered to be in z direction of the plane of this paper. Since this is 2D, everything here is going to be off the plane. Consider that the counterclockwise to be positive. Okay? Now, we're going to apply that into this system. So let's take into consideration the different moments that cause this to rotate counterclockwise. The first moment is the moment of the external force, external torque, from 0 to 4 at time dt, right? The second one is the moment of the 10. Okay, so this is going to cause to r cross 10. This is distance 0.5 and this distance 0.5. So this is r cross f, and this is the angle is 90 degrees. So it is going to be integration from 0 to 4 r cross f 10 multiplied by sine theta, sine 90 0. So sine 90 is 1 dt, right? This is for this part, and it's a positive because it's causing it to rotate counterclockwise. Same for that one, 0 to 4, 0.5 multiplied by 10 sine 90 dt. This is the summation of this equal what's happening after. This is r cross mv for the system, right? So I have two particles, two masses. For the first one, it's r cross, so mv, so this is equal r mv sine 90. Therefore, it is r by the mass 10 by the velocity of this particle, which is v2, right? And it's also going to be positive, plus 0.5 for that one multiplied by mass multiply the velocity of that, which is the same as this velocity, call it v2, right? Minus this part over here, which is r cross mv, since velocity is at rest position, so this becomes 0. So what we have here, we have 8 over 2 t squared from 0 to 4 plus these are equal, so this 2 by 0.5 by 10 by 1 by the distance over the time difference 0 to 4, because integration of a constant is t, I'm sorry, yeah, it's t, and then you substitute, become 4 minus 0, right? And that is equal, these are identical, so 2 by 0.5 by 10 by v2. So that's the equation that you got there. Let's take a look at the attention quiz and then conclude our chapter. Consider a ball is traveling on a smooth surface in a 3 feet radius with a speed of 6 feet per second. If the attached cord is pulled down with a constant speed of 2 feet per second, which of the following principle can be applied to solve for the velocity of the ball when the radius changed from 3 feet to 2 feet? So we have a ball attached to a cord being pulled by a force. So the cord has a tension, and that is the curve or the path of the ball. It goes from R1 at 3 feet per second, 3 feet with a velocity of 6 feet per second, and change into R2, 2 feet, what is the velocity, v2. Now what causes this is that force, and this force, as you notice, is in the direction of r. So the angle between r and the force is 0, and so the moment of this force as computed to an O, a point O, is going to be r cross f, right? And this is equal as a magnitude r, magnitude, which is 3 multiplied by the force F, whatever force, multiplied by the angle between the F and the force. The angle between the force and F, in fact, we're looking at this force, right? Because it's a tension. So the angle is 0, therefore sine 0 is 0. So the moment of this force is 0 here and also 0 here. Okay, so and since we are only having one particle, so I can say summation of the moment from t1 to t2 dt, right, equal to, if I compute the angular momentum change about O, the moment of this force is going to be 0. So the angular momentum at radius r1 is equal to the angular momentum at radius r2, right? And this is simply is r cross mv1 equal r2, I should say this here, for mv2, right? And since the r and the v are orthogonal, so sine 90 is 1, so I can say it's equal to r m v1 equal to r2 m v2. It's same mass cancel, so I don't need to know anything about mass. So r1 v1 equal to r2 v2. Alright, so which means is 3 multiplied by 6 is equal to 2 multiplied by the unknown, so V2 is equal to 3 by 6 over 2. That's going to be 3 by 3 equal to 9 feet per second. With this example, we finish chapter 15. And there's one group problem solving. You can try it at home. It's a simple one. Now, next topic is a new topic. We move from particle into rigid body, translation, rotation, kinematics, and kinetics. I'll post some assignment, and I will see you next lecture.